So welcome back, everybody, to Math 210, Calculus 1. And it's time to have another test. According to the syllabus, that's going to be today, but I think that's a little premature. I'd like to do it on Wednesday, and I think that having a test over a chapter makes sense. So our first test was on Chapter 2, and it makes sense to have our second test on Chapter 3. And we're almost done with Chapter 3. What's the story of Chapter 3? It's the definition of the derivative. So there's, the definition with x goes to a or with h goes to 0. I would memorize those two definitions. We also did things like using the limit definition of the derivative to find the derivative of like f of x equals x squared or f of x equals 1 over x. Those are common test questions. A bread and butter test question is given a function, find the formula for the tangent line going through whatever point. So that's just requiring you to know how to find the derivative at a point. And then plug that into the point slope formula line. Yeah, there's a question on what about manuscript 2? I think that like my feeling for just pandemic teaching and my read on how everything is going is that my feeling on that is to only have 2 manuscripts instead of 3. I think that's a pretty good compromise. I'd rather have the same number of tests and I just feel like having 3 manuscripts and the however many tests with the homework together just feels a little tight for this semester. Since we're not able to do like on-campus office hours and things like that. So what I'd like to do is cancel manuscript 2, but try to hold the line on test 2, so that, which I hope is good for you guys, because you've had a chance to have a test with me and get feedback, and then take a second go at it, which was really good. So I think you've got some experience now, like understanding the kinds of things I'm going to ask and how I'm going to ask you to justify your answers. So we'll do something for manuscript 3. Other things that you need to know are how to take derivatives of functions using the product rule, using the quotient rule, and using the chain rule. So there'll be one question on using the definition to calculate something, to calculate a derivative. There'll be one question on find the tangent line through the point. There'll be one question that just says calculate these derivatives, and you'll see like a quotient. Well, you have to use the quotient rule. You'll see a product. You'll see something where you have to use the chain rule, right? And just making sure that you know those formulas. You know the formula for the derivative of like 2 to the x. That was something that I asked you all to watch the video on instead of me lecturing on. So thank you for accommodating that. But if you see something like f of x equals 2 to the x, make sure you know that this is really just natural log of 2 times 2 to the x. So make sure you're not tripped up by forgetting some formula. And I think that being able to use the chain rule to show why this is true is also important. So like if So being able to go through the process of saying like 2 to the x is like, how do you do this? Do you say this is like e to the natural log of 2 to the x? I think that's how we do that. Remember that e and natural log are inverse functions, so that for any y, e to the natural log is equal to y. So 2 to the x is equal to e to the natural log of 2 to the x. You can do this so long as this number is positive, and 2 to the x will always be positive, because natural log only takes positive inputs. And then if you know your logarithm rules, you know you can bring down the exponent and rewrite this as e to the x times natural log of 2. So that's where that constant comes from. I guess I'm kind of redoing my video lecture, but that's okay. So if you want to calculate the derivative of 2 to the x, then it's the same thing as calculating the derivative of e to the x times natural log of 2. And this is like e to the g of x, if you like, where g of x is natural log of 2 times x. I've got to write more on the left-hand side of the board, because on the right-hand side it doesn't show up as well for you. So when you're calculating this using the chain rule, you get is derivative of e to the x, which is e to the x, plugging in x natural log of 2, and then you're multiplying it by the derivative of g, which is just natural log of 2. And then what you do is you just rewrite this. You rewrite this back as e to the natural log 2 to the x. It's natural log of 2. And so you just get 2 to the x times natural log of 2, for instance. So, I mean, now that you know that, if you just see natural log of, if you just see 2 to the x, you'll know the derivative is natural log of 2 times 2 to the x. But I do think it's important for you to know the process. Especially for online proctored tests, you're not going to see me ask you a lot of questions where you can just look up the answer. You'll see me asking more about like process, like what's going on. So testing, like, can you go through this derivation, is more useful to me than testing whether you can recall the formula. So that's like an application of the chain rule. And then the other thing that we did was implicit differentiation. So there will be an implicit differentiation question. We covered that last Wednesday. That's what happens when you're given an equation, usually a two-variable polynomial like x squared plus y squared like equals x squared plus y squared plus 4 equals 0 or something. Can you figure out dy dx using the chain rule? There'll be a problem like that, and we also figured out formulas for the trig derivatives using that trick of drawing the triangle. There may or may not be a problem on something like that. Like, can you figure out the derivative of, like, I could ask you to go through the process of finding out the derivative of like arc secant or something. And finally, there's this issue of related rates. And there was a related rates question on the homework, but there's also this, this section, this brief section, chapter 3.10 on related rates. And so like I mentioned in the Google announcement, this is not really a separate topic. It's not really a topic like the chain rule or the product rule. This is just, it's just a bunch of word problems that they kind of amalgamate together in one section It's just a bunch of word problems to help you practice the implicit differentiation or the chain rule. So it doesn't really need lecturing per se, but what we can do is go over some problems. And you saw a video on one problem at least. And what I want to do is track through a couple of these examples, look through some exercises in the book too, to make sure you've got some practice on this related rate stuff. And you may see something very similar on the test. Okay, so let's get into it. And stop me with any questions. So this is example 3 on page 200, if you want to follow along with me. So this is called the sliding ladder problem. With all of this stuff is going to go back to drawing a picture, which is usually going to be a triangle, and you're usually going to solve this either with similar triangles or with the Pythagorean theorem, as we'll see. So a 5-meter ladder leans against a wall. So here's our wall, and here's our 5-meter long ladder. The bottom of the ladder is 1.5 meters away from the wall at time t equals 0. So at time t equals 0, the bottom of the ladder is 1.5 meters away. I'll call this distance x. And I'll say something like x of 0 equals 1.5. And further than that, the ladder slides away from the wall at a rate of 0.8 meters per second. So you're sliding away from the wall in this direction at a rate of 0.8 meters per second. So this distance x from the wall to the base of the ladder is changing by a rate of 0.8 meters per second. So really what's happening is you're saying that the derivative of x is equal to this constant 0.8 meters per second. By the way, you can put these two facts together. The only functions whose derivatives are constants are functions of the form mx plus b, where, or like in this case, you might say x of t equals m times t plus b, because it's a function of time. And the derivative is, of course, m, which is 0.8 in this case. And the constant b, that's what happens when you plug in t. That's given to you as like 1.5. So although this isn't needed to do this problem, I'm just pointing out to you that when you've got like the derivative equal to a constant, you've got a linear function, and as soon as you know like one value that you can plug in, like that'll tell you b. Okay, fine. So like what's the actual question? The question is, find the velocity of the top of the ladder at time t equals 1. So find the velocity of the top of the ladder at time t equals 1. So here's the top of the ladder, and this top of the ladder is sliding down. Let's call this vertical distance y. So y is the distance, and velocity is distance over time. So velocity, in fact, is the derivative of distance. So I'm trying to find velocity at the point t equals 1. So half the battle with this stuff is actually writing down the quantities that you want to find, because it's not presented to you this way in the book. It's presented as a word problem, and you need to be able to draw a picture and label the relevant quantities, and then be able to write down an expression for what it is that you need to find. So what's the velocity of the top of the ladder after 1 second has passed, you're trying to find dy dt at t equals 1. So how do you solve this related rates problem? You're given one rate, so you're given one rate of change, the derivative of x. You're asked to find another rate of change, the derivative of y. The way that you can do that is you find an equation relating x and y and then use implicit differentiation. Are there any questions on the setup of this? Because it's important to let you ask questions on the setup, not just the final conclusion. Okay, well, feel free to ask questions at a later time if you like. And so like I mentioned, all of this usually goes back to similar triangles with the Pythagorean theorem. Here we've got the Pythagorean theorem. The relationship between x and y is that x squared plus y squared equals 25. So I suggest writing down that equation somewhere. I'm not doing like a great job of presenting my answer exactly like I would on homework or tests. I'm kind of like doing board work, writing equations and explaining at the same time, but you will need to write down the equation. Like in this case, x squared plus y squared equals 25. And it would even be better if you had like a sentence that kind of explains, by the Pythagorean theorem, x squared plus y squared equals 25. Of course, I'm just saying it in words. And you want to find dy dt at the time that t equals 1. Or if you don't like Leibniz notation, you could also write this as y prime of 1. So like, what is that? Let's differentiate this equation with respect to time. And what you're going to get is 2x times x prime. So that's the chain rule, isn't it, right? X is a function of t. You've got x squared. So the derivative of x with respect to x is 2x, but the derivative of x with respect to t is 2x times x prime. And the derivative of y squared with respect to t would be 2y times y prime. And that's all equal to 0 because the derivative of a constant is equal to 0. And you can now just start plugging things in. So you're looking at this specific example, you're looking at t equal to 1. So when t is equal to 1, x of 1 is going to be what? It's going to be 1.5 plus 0.8. So that's going to be what? 2.3? And then y would be, well, you could use this equation to figure out y, because 2.3 squared plus y squared equals 25. So y is equal to the square root of 25 minus 2.3 squared. I don't know what that number is. You'd use your calculator for that. You can both check it out. So I'm getting 25 minus 2.3 squared is equal to 19.71. And when I take the square root of that, I'm getting 4.4395. So I'm going to estimate this as y is roughly equal to 4.44. And x prime is equal to 0.8. So I think we're good, right? I think we can take 2 times x, so that's 2 times 2.3, times x prime, which is 0.8, plus 2 times y, which is 4.44, times y prime is equal to 0, and now you can just solve this equation for y prime. And it'll automatically give you y prime at t equals 1, because all the things that we've plugged in are at t equals 1. And I'll even, you could do this with a calculator, but I'll do it on Desmos and show it to you. I think there's lots of different ways to do this problem. I may show you another way to do it too. And I do all of this stuff honestly, and what I mean by that is I don't prepare in advance. So if I make a miscalculation, then you'll just see me do that, and we'll have to fix it together. Okay, so just take care to also check me. So what was it? 2 times 2.3 times 0.8 plus 2 times 4.44 times y prime. Desmos isn't going to let me use y prime, so I'll just use x, and that's equal to 0. And so what was negative 0.414? So it gave me x equal to negative 0.414. And this is a rate, and of course x on Desmos means y prime. So I'm getting 0.414 meters per second, and the negative sign is because it's falling downward. So I'm getting that y prime of 1 is roughly equal to negative 0.414 meters per second. And I'll check the book to see if it agrees. And I always hate doing that because it's like finding out if I'm making a mistake. But here it looks like the book agrees with me. The book has used different notation to label the variables, but so you can check out their explanation too. Are there any questions about how I did that problem? So I want to show you how to do this actually another way that's similar but not exactly the same. So we used implicit differentiation. We wrote down the equation. X squared plus y squared equal to 25, and we differentiated that with respect to time. We also could have sort of solved for y squared and said like y squared equals 25 minus x squared. And I guess we could have said that y is equal to the square root of 25 minus x squared. I know it should be, to be formal, it should be plus or minus, but since y is this positive distance, it has to be plus. And you could also just calculate y prime and then plug in t equals 1. So you could calculate dy dt directly. But you would have to use the chain rule in order to do that. And so when you do that, you'll get, you'd be using the chain rule with like f of x equals root x, and with g of x equals 25 minus x squared. And so when you do that, you get the derivative of root x is 1 over 2 root x, but then you plug in 25 minus x squared. And then you multiply by, you multiply by the derivative of the inside function, which is a derivative with respect to t. So what's the derivative of 25 minus x squared with respect to t? it's going to be, well, derivative of 25 is 0, and derivative of negative x squared is minus 2 times x prime. And the 2's will cancel for you. And then you'll be left with plugging in what happens at t equals 1. So when t equals 1, we figured out that x was 2.3, so you would get minus 2.3. And x prime was given to us as 0.8. And then you'll just be dividing by the square root of 25 minus 2.3 squared. And that should look awfully familiar. So like if you solved our equation for like y prime, then this is the calculation that Desmos did for us. And it was like minus 0.414 or whatever. So it's just the difference between solving this equation first or not. It doesn't really matter. I kind of like to leave the equation like this and then just start differentiating and using 2x times x prime plus 2y times y prime equals 0. Because it lets me just do some work without having to worry about like more algebraic manipulations. So I want to show you some more stuff, and this one I'll try to go through a little bit quicker. Example 4, tracking the rocket. That's actually a very similar example to what I did in my video with the balloons on the house. It's just a rocket instead of a house floating upward. So, and the numbers are changed a little bit. So I'm going to skip example 4. Please, you can read that on your own or reference my video, which does something very similar, talking about a change in theta versus a change in y. And let's do this example with the person. So this is example 5 on page 201 if you want to follow along. So this is a person on a tractor. It's kind of hard to explain what's going on here. So you've got this stand attached to the ground with a pulley. You've got someone on a tractor that's lifting a bale of hay up. And the way that they're doing it is, so here's the person on the tractor. They're driving this way, and they're pulling this rope, which then the horizontal force through the pulley lifts up the hay. And so here's a diagram that's sort of given to you in the problem statement, that this length is 4.5 meters. This length we're calling x. The distance from the hay to the ground we're calling h, and this is a 6 meter high pulley, so therefore this distance has to be 6 minus h because they add up to 6. Okay, so the tractor travels at 3 meters per second. We're given that the tractor travels at 3 meters per second. Pulling a rope attached to a bale of hay through a pulley. So with the dimensions as indicated in the figure, how fast is the bale rising when the horizontal distance is 5 meters? So what are you being asked? You're asking how fast is the bale of hay rising when you are 5 meters away. So you're being asked for h prime. So you're being asked for the change in h, so dh dt, at the point when x is equal to 5. And you're also given that the rate of change of x with respect to t is 3 meters per second. And so you're given x, and you're trying to find, well, you're given the rate of change of x, and you're trying to find the rate of change of h. So you need an equation that relates together h and x. Right? And what if you immediately go to Pythagorean theorem, you're going to get that x squared plus 4.5 squared is equal to this, length of hypotenuse. I mean, I'll call it h. But that's fine, that's true, but it doesn't relate x to this quantity, 6 minus h. And that's really frustrating and kind of, a stumbling block for doing the problem. I can tell you the way to proceed, but I'll let you look at it for a second. Like, do you have any suggestions? Like how where in the picture, like, how can we use this picture to relate x and this little h together? Yeah, that's kind of a it's kind of a hard problem, isn't it? And the reason why it's kind of hard is because there's something that's given to you in this problem that hasn't been directly specified, which is you're pulling a rope, right? And the length of the rope doesn't change at any point, right? So your distance x can change as you're moving the tractor this way and you're lifting this up, of course, but the total length of the rope doesn't really change. So let's call, I don't know, and we don't know what that is. So let's call that L. Let's use L for the total length of the rope. And that total length is actually this distance, capital H, plus this distance 6 minus little h. So L is actually equal to h plus 6 minus the height, which is telling us that, well, h is also equal to x squared plus 4.5 squared by the Pythagorean theorem. So that's telling us that x squared plus 4.5 squared plus 6 minus h is equal to this unspecified number, L. And that's the secret, because now you have a single equation that relates x and h. And now you can just do this by taking a derivative, finish the computation in the usual manner. Because if you now take the derivative of both sides with respect to t, here's the nice thing, the derivative of the constant is equal to 0. So you never see this L again. You don't need to know its value, because the derivative of a constant with respect to time is equal to 0. On the other hand, you've got 2 times x prime plus derivative of 4.5 is equal to 0. Derivative of 6 is equal to 0. Minus h prime of t. And that's all equal to 0. So what I'm getting here is, solving for h prime, I'm getting that the derivative of h with respect to t is equal to 2 times x of t times x prime of t. And you're given that x prime of t is a constant, it's equal to 3, and you're being asked to calculate this at the point when x is equal to 5. So you're calculating this at an unspecified time, but at that unspecified time, x is equal to 5. So perhaps a better way to write it is dH dt with the vertical line and just say that x is equal to 5. But when it's true that x is equal to 5, you'll have 2 times 5 times 3, because the derivative of x is equal to 3. So you're going to get 30. And it's in meters per second. Don't forget the units at the end, like all your measurements were in meters, time is in seconds. So the derivative, distance over time, give you meters per second. So I'm seeing that this bale of hay is being lifted up at a rate of 30 meters per second. And the book's telling me that I got that wrong. Why did I get it wrong? Oh, I see. I got it wrong because h is actually the square root. It's actually the square root of that. So x squared plus 4.5 squared plus h squared is equal to h squared, excuse me. But the length of the rope is actually h plus 6 minus h, 6 minus little h. So this actually, I should have said L is the square root of x squared plus 4.5 squared. So that makes this a little bit more complicated. Let me actually redo that so I get the correct answer for you. But the principle is still quite good. Let me actually redo that. So taking this derivative with respect to time, just using the chain rule, it's 1 over 2 times x squared plus 4.5 squared. You see me doing that quickly, and then times the derivative of the inside function, which is 2x times x prime. You see me doing that quickly because I know the derivative of the square root of x is 1 over 2 root x. Then I'm plugging in the inside function and taking its derivative. Then I'm adding to this. Derivative of 6 is 0. Derivative of negative h is minus h prime, which is still equal to 0. So this is equal to h prime of t now. So it's just this extra factor that I kind of missed. So now when x is equal to 5, you get 2 times 5 times 3. So you still get 30 on top, and now you're dividing it by 2 times the square root of x is 5, so it's 25 plus 4.5 squared. So this is actually your answer for h prime. And when you plug that into the calculator, this is roughly 2.23 meters per second. Yeah. So apologize for that typo there, but it's not a huge deal. I'm not too concerned when I make a typo or when you make a typo, just as long as you're showing your steps or explaining your work. And really the thing that I'm more interested in here is, can we set up the problem correctly using a diagram? Can we label our variables and then write an equation that relates those together? So any questions so far? So the question, why is 6 minus h equal to h prime of t? 6 minus h is not equal to h prime of t. It's absolutely not equal to h prime of t. What I'm doing is I'm taking this equation and differentiating both sides with respect to t. So if two quantities are equal, then their derivatives are equal. So the derivative of this left-hand side is equal to the derivative of L. So therefore, 0 is equal to the derivative of this. And the derivative of 6 minus h is equal to negative h prime of t, just because the derivative of 6 is equal to 0, and the derivative of negative h is negative h prime. That's what I'm bringing to the other side and setting that equal. Cool. So other questions or comments? All right, cool. Let's go through, and I want to actually just pick out some problems from the book at random. Maybe we have time for at least one more. Let's do. I mean, they all relate to using a triangle to make an equation. Let's do one more. I'm going to pick number 17. Just sort of picking these at random from the textbook. So a person that's 1.8 meters tall walks away from a 5-meter lamppost at a speed of 1.2 meters per second, as indicated in the figure. So you've got a 5-meter lamppost, and you've got someone walking away from it. So this person is 1.8 meters tall. Find the rate at which the person's shadow is increasing in length. So this person is walking at a speed of 1.2 meters per second. So let's call the person's distance to the lamppost, let's call that x. So here's a lamppost that's, shining light. And you're walking this way away from the lamppost. You're 1.8 meters tall, and we're given that you're walking at a speed of 1.2 meters per second. So whenever somebody gives you like a rate of change, you can know that's going to be the derivative. So you're walking away at a speed of 1.2 meters per second, and then how fast is your shadow increasing in length in front of you? So like, what is your shadow? Kind of by definition, if you look at this ray of light that comes out and hits you right on the head, then all the light above that is going to be continuing on, and everything else under that is going to be blocked. So if you let this first light ray that is allowed to escape, that's going to come down the same angle and then hit the ground. And now this is going to be the length of your shadow. Let's call that y. So the length of your shadow definitely depends upon how far away you are from the lamppost, because as you walk farther and farther away, basically this hypotenuse is this angle here is getting bigger and making that shadow tend towards, get longer and longer as you start walking away. So you're given x prime, so you're asking for what is dy dt. So this is part of doing the problem, is labeling the variables and writing down the expression of what you're being asked for. Find the rate at which the shadow is increasing in length. So this is what we're being asked for, and we're giving something in terms of x. And therefore, what we need to do is we need to find an equation that relates x and y. If you just try to rely on Pythagorean theorem, I don't know, like 1.8 squared plus y squared is equal to that length, that doesn't really help too much. There's no Pythagorean theorem here. I guess what you could do is like this big triangle, so like x plus y squared plus 5 squared is equal to this length. But then the problem is you don't know the length of the hypotenuse, so that's kind of like a non-starter. So what you can do here, if you remember like geometry or trigonometry, is you can use this principle of similar triangles. So what are similar triangles? Similar triangles have the same angles. It's two triangles with the same angles. And when you have two triangles with the same angles, they must be equal to each other, except one is scaled up from the other one, which means that all the ratios of their sides have to be the same. And so, in other words, like if I take this small triangle and compare it to the big triangle, the three angles are the same. Like there's a right angle here, this angle is shared, and these two angles you can see from, you can see from the picture are the same I mean, you can prove it too, because like the angles have to add up to 180. So if one of them is a right angle and one of them is a shared angle, then the other angle has to be the same. So like these two triangles are similar, and then therefore the ratios of corresponding sides have to be equal. So if I take y over 1.8, like y over 1.8, then the ratio of corresponding sides must be the same. So what are the corresponding sides for the big triangle? It's going to be x plus y divided by 5. So y over 1.8 should be equal to x plus y over 5. That's what I'm getting from similar triangles. And you can now solve this equation for y and take its derivative. Or you can just start taking a derivative like right this second, because if I have two things that are equal to each other, their derivatives must be equal. So taking the derivative with respect to time, I'm going to get just y prime over 1.8. I've had students, try to use the quotient rule here. You can use the quotient rule, it's true, but this is just a constant. So it's just like 1 over 1.8 times y.
Your mic cut out.
So its derivative is just going to be y prime, times that same constant. Like save you some energy there. And then the derivative with respect to time here is just going to be x prime plus y prime over 5. And we're given the derivative of x prime. That was we're given the derivative of x, so that was 1.2. So I can kind of just fill that in. And say that y prime over 1.8 is equal to 1.2 plus y prime over 5. And I can now solve this for y prime. And then I'm finished. And let's just use Desmos to solve it for us, because we're about out of time, but I at least want to show you a real numeric answer. And Desmos won't accept y prime, so I'll just use like x in place of it. So like if I say x over 1.8 is equal to 1.2 plus x, and then the entire quantity was divided by 5, right? That's what it was. Then the answer is 0.675. You can also just solve that by hand by solving for y prime, or solving for x as it is listed there. So this is telling me that y prime is 0.675 meters per second. So that's how fast your shadow's changing at that. That's how fast your shadow's changing as you're walking. And I have no way of checking that right this second, so hopefully I didn't make a mistake, but that's my answer to that problem. So general strategy, you're given a related rates problem. Can you draw a picture that illustrates what's going on? Can you label the quantities involved? Can you write down an expression detailing what you want to find? And then can you use probably Pythagorean theorem or similar triangles to give yourself a relationship between your quantities, in this case x and y? Then just take derivatives of both sides and plug in your information and solve for the quantity that you want. That's the secret to related rates problems. Be welcome to get in touch with me. And that's all for today. So I'll put up maybe another practice test online to give you an idea, but it's the same deal as last time, 4 or 5 questions, and I went over probably what I'm going to ask. And about how much detail you need to show in order to get an A. So yeah, thank you for your time and attention, and we will see you in 2 days.
Thank you. Have a good day.
Thank you.